So good afternoon to you all, and welcome to our August edition of the AESIN Tech Talks. I'm delighted to have Daniel Murphy, Dan from ST Microelectronics present today. I've spoken to Dan a few times over the last few months, and every time I speak to Dan, I'm very impressed by the by the work that that's the wind blowing today. By the work that ST Microelectronics are doing in the area of power electronics, amongst other things. So it was a great opportunity for me to get Dan to come and talk about some of the work that they're doing. So Dan's the principal technical marketing engineer at ST Microelectronics. The talk title is Key Power Electronics Trends in EV Traction Inverters. And that's a big topic at the moment. I've talked to a number of companies, number of members who are keen to see what else AESIN could do in this space. And I think there's an opportunity for us to create something quite interesting as a community around power electronics and automotive and the automotive industry. So if there's anybody interested in that topic, please drop me a note and we'll make sure that you're involved in any future discussions on that as we look to set up an interest group around that. So I'm going to let Dan introduce himself and the company as well as part of the presentation. Just to say, once Dan finishes, I'll hold a short Q&A. We'll take 3 or 4 questions. So please make a note of any questions that you think will be quite interesting to ask Dan. And then we'll wrap up just with some information about upcoming events as well. With that, Dan, thanks very much again. And I'm going to hand over the platform to you.
Okay, thank you. Thanks. Right, can everybody see my screen okay? Is it clear?
Yes.
Yeah, very good. So thank you for the introduction, Gunny. Yes, as you mentioned, this is an incredibly important area for ST. So we're always wanting to have dialogue with people, whether that's car makers or tier ones, universities, third parties, because the more information we can capture about these types of trends, the more appropriate the product mix and the roadmap we can develop. So what we'll do today is just go through some of the high-level items with regards to the power electronics. So quickly talk about the market and the ecosystem evolution, some of the opportunities and challenges in inverter design. We'll then look at multiple motor concepts. So this is quite important. So there's 2 or 3 slides on that. The adoption of 800 volt, which is very important to cover as well, particularly as from about 2024 through to 2026, this becomes quite prolific. Then we'll look at the implementation of power semiconductors into traction inverters and the different ways that can be done. We'll move on to talking about scalable discrete packaging, because this is a very strong trend that we see with car makers and tier ones in current projects. From there, we'll move on to look at some of the new methods and approaches. So this is quite important, and I'll talk a bit about this later on in the presentation and why it's so important. And then we'll finish with some key takeaways, and we can have some questions as well and some discussion if it's interesting for people. Okay. So first of all, the reason electrification is so important to ST is very obvious on this slide. So you can see by 2028, the market's worth approximately $26 to $28 billion to ST. If you look at the breakdown, this is predominantly coming from traction inverters and batteries. So if you look at the bar chart on the bottom left-hand side of the slide, it's clear that these 2 areas are really driving the innovation in electric vehicle subsystems. Then on the right-hand side of the slide, you can see the average dollar content of a combustion engine car is approximately $500. As we move towards a battery electric vehicle, this increases to $1,300. So the reason this is so critical is what it's doing is it's breaking the connection between passenger vehicle volume and the opportunity for semiconductor companies. So previously, if more cars were produced, semiconductor companies generated more business. But today, because of the content per vehicle, we don't necessarily need an increase in passenger vehicles, full stop. We just need the widespread adoption of electric vehicles to continue. So if we look at the ecosystem, so if you look on the left-hand side of the slide, there's this old pyramidal approach where we have the car maker sat at the very top of the triangle. And then we have tier ones, tier twos, and semiconductor vendors. And in the past, this has been quite a rigid approach, a straight line running through the different tier two, tier one towards the OEM. So this is completely changing. So if you look at the right-hand side, what we have now is we have vehicle manufacturers sat right in the middle, and you have semiconductor suppliers sat around the outside together with tier ones, tier twos, third parties. So what's happening with the introduction of electric vehicles, this also makes the adoption of more simple chassis electronics possible, autonomous driving. So everything is changing for car makers. So we expect by, for example, 2030, at least 60% of the propulsion systems in cars will actually be developed by the car makers. So that's quite a strong transition across from what we saw previously. The other reason for this type of model evolving is car makers are wanting to somehow drive the innovation and the technology more than they did previously. And what's also key, and it's the last point on the text at the bottom, is it's about securing supply. So components such as silicon carbide and perhaps in the future gallium nitride are going to be difficult to come by, but just because of the rapid growth, it's difficult for silicon vendors to keep up. So car makers are trying to engage more directly with silicon vendors to secure supply. So now looking at some of the opportunities and challenges. So we have the increase in battery voltage, which we'll talk about in more detail later. So obviously this allows for increase in power. So as you go up in voltage, you can go down in current. So cabling can be lighter and easier to implement into the vehicle. And also it facilitates faster charging. New motor technologies such as axial flux motors, synchronous reluctance motors are coming on stream, but these require better thermal management, and in the case of synchronous motors, rotor excitation. Then the third point is reducing switching losses and system cost. So higher working junction temperatures. So 200 degrees C, particularly for silicon carbide, is becoming more commonplace. So here the challenge is we need some kind of extensive analysis to optimize the cost in terms of the switches that are used. So improve thermal and electrical performance through new packaging. So here the challenge is the system integration, and sometimes the cost of adopting these new approaches can be challenging. So now moving on to the motor concepts that are adopted in vehicles. So on this slide, you see a single motor concept and a dual motor concept. So for the single motor concept, on the rear axle, we have an inverter, which is based on silicon carbide for both 400 volt and 800 volt bus systems. And then on the right-hand side, you see a dual motor concept. So this is becoming more commonplace. So what you have here on the rear axle, you have a silicon carbide based inverter for partial load. And then you have a boost inverter on the front axle, which is based purely on IGBTs, where you need a high level of RMS current running through the vehicle. So this is, for example, if you're pulling a caravan up a hill from start, you obviously need huge amounts of phase current. But if you're running around town, you will only be using the partial load motor that's on the rear axle. So the advantages this approach brings, so there are some mechanical advantages. So it can help with the weight distribution within the vehicle, and also some system and component downsizing. And there's also obviously the opportunity for backup somehow if you have two inverters in the vehicle. The electrical advantages are obviously this hybrid approach where we're using two different technologies. So we make use of silicon carbide technology and the very low switching losses that brings for partial load operation. And then for the boost function, where we have very high RMS current, and it's mainly the static losses that come into play. We can leverage IGBT technology, which is less expensive and still performs very well where static losses are concerned. So looking at the commercial advantages, there's no need for a single large inverter. So this is actually the main benefit. So if you consider a larger vehicle, a large SUV, for example, if you only put one motor into the car, you have to dimension the inverter for every single possible scenario. So as I mentioned before, if we're trying to go from stationary position to pulling something up a hill, you need to dimension all the silicon carbide for this use case, when the reality is 95% of the time the inverter won't even be delivering 20% of its total load current capacity. So this is the main commercial advantage here. So partial load motors as well can be based on silicon as well. So IGBTs still have a strong place in this type of product. So one of the most important trends, without a doubt, is the adoption of 800 volt bus. So if we go back a few years, it wasn't particularly clear if this was really going to gather any kind of momentum. But what seems to have driven it is actually the demand for fast charging. So we can obviously charge vehicles much quicker if we run at a higher bus voltage. So we go up in voltage and down in current. So we're benefiting from dual loss reduction by doing that. If we go up in voltage, there's obviously power increase. So if we keep the cabling in the vehicle the same and the level of current the same, the power goes up together with the voltage. And then this can also lead to easier integration and cost weight reduction. So cable harnesses in vehicles are a big problem for car makers. So in an SUV, a cable harness can weigh 125 kilograms. So there's a strong motivation to reduce the weight of this. So 800 volt, what it's also doing, and it's helping ST tremendously in this sense, is as we go up in bus voltage, the benefits of silicon carbide become more prolific. So this trend is helping with the adoption of silicon carbide into EV subsystems. So if we look at the bottom of the slide, you can see here the benefits of implementing silicon carbide. So for a 400 volt, 160 kilowatt system, we have about a third of the semiconductor area is actually needed, and we can realize an improvement in efficiency of approximately 5%. So this is very good. And as we go up in voltage, the benefits just become even more prolific. So you can see 1/5 of the semiconductor area is needed, and we have 8 to 12% efficiency gain. So we'll just quickly go through this slide. It's very colorful, and what it's basically showing us is we did an exercise of looking at all the European car manufacturers and when they're planning to adopt 800 volt. And you can see here 2025, 26 is the real sweet spot. So as we move through 2025 into 26, everyone is pretty much running on 800 volt bus. And there's a similar trend in also China and the US. So now here we look at semiconductor considerations for different motor technologies. So here I've just picked 4 different types of motors. So we got permanent magnet motors, in-wheel motors, axial flux motors, and electrically excited motors. So for the permanent magnet motors, there's very good performance on partial load cycles with silicon carbide. However, the trend is to try and reduce the use of such motors because of the rare earth materials that are inside them. Then for the in-wheel motors, so this environment is completely different. So the motor is inside the wheel, so it's very near to the brakes, for example. So there can be some more extreme shocks and temperatures that need to be managed by the power electronics. And also there's a desire to increase the switching frequency to downsize the form factor of the inverter. So again, this really helps is helped with the use of silicon carbide. So axial flux motors have very good power density and are very compact. They can also achieve very high dV by dt. So what we can do with these types of motors again is leverage higher switching frequencies. So yet again, the use of wide bandgap materials is very interesting. Then finally, for electrically excited motors, so this is the motor that would be used as the boost motor in vehicles. So I know of at least four car makers that adopt this approach. And here we can leverage IGBTs, for example. So we can use lower cost switches. So one of the downsides is we obviously need additional power switches for the rotor excitation. So here, how do we actually get the semiconductors into the traction inverter? So what I've tried to do is summarize 3 approaches here. So on the left-hand side, we have bare die. So the benefits here are you have complete flexibility. So if you develop your own module, you can define the die size that you want. You can define the pad geometries. You can define where the pads go on the die and the metal stack. There's a huge degree of flexibility with bare die, but developing modules is also very complicated. So if we move to the far side of the slide, you have a complete module. So this is the least complex way of introducing the power semiconductors into the inverter. So you essentially have all 3 phases addressed with this module. It's approved to AQG 324 already, and it's very established and reliable. So nearly all of the electric cars you see on the road today are running with this type of solution. Hyundai Ioniq, VW, ID3, ID4, all have this type of approach. So in the middle is what we see as the future, so transfer molded packages. So one of the main benefits here is we can leverage a higher junction temperature, so we can run up to 200 degrees with this approach. By putting discrete molded packages in parallel, we can reduce the inductance in the commutation loop. So there's one project we have running in ST, and we're realizing less than 2 nanohenries, for example. Then the final and one of the most important benefits is the reliability. So these types of components can be sintered onto a cooler, and we can have a very good degree of reliability. So to give you an example, a module like you see on the right-hand side might be 70,000 cycles. And for the molded packages, we're achieving results in excess of 300,000 thermal cycles. So here, this is looking at the transition that I was talking about a little bit on the previous slide. So you can see here the move across from traditional modules to discrete components and transfer molded modules. So here, the main benefit is it's highly scalable. Very good junction to case parameters can be realized. It's very compact. We have high reliability and very good short circuit withstand times. So this is really the headline trend that we see. So if we move on to the next slide, you can see an example of this. So in this slide, we're showing the dimensioning for an inverter that would be using ST-Pack. So on the bottom left-hand side, you can see the bus voltage, the switching frequency of the inverter, and then what you can see in the table is the RMS current that can be realized if we have 3, 4, or 5 ST-Pack per switch connected in parallel. So this gives a good example of how scalable this discrete approach is. And also, again, it's important to highlight the reliability. So sintering transfer molded components onto coolers. You're sintering on components that inside have clips connected to the die rather than wire bonds. And high pressure silver sintering is very good in terms of performance where thermal shock is concerned as well. And also mechanical shocks, so vibrations, that type of thing. So looking at the new methods and approaches, so we have embedding. So what this is where we embed the actual power switches into the PCB. So instead of them being in a module or a package, they're actually directly integrated and housed into the PCB. So here, as well as significantly reducing the parasitics because we don't have any wires or interconnections, the data in terms of reliability is highly promising as well. Then we have direct liquid cooling. So looking at the sharing of coolant systems for mechanical and electrical elements of the propulsion system. And then finally, and without a doubt, the most important is just looking at alternative topologies. So T-type topologies, neutral point clamp. So here we're essentially going up in the number of switches that are being used. And if you purely analyze the content in terms of power switches, the cost can go up. But what it brings is improved system efficiency. So car makers are interested in the battery and the motor. So if spending another $50 on power switches brings better efficiency, better motor efficiency, longer range, then that is the direction they will go in. So the final slide. So the key takeaways really from the presentation are the proliferation of 800-volt bus that we discussed earlier, the evolution of the ecosystem where car makers are becoming more heavily involved, the adoption of scalable discrete packaging, and the development of innovative packaging. So silver sintering, direct embedding that we mentioned on the previous slide. And then the final takeaway is the introduction of new topologies. So I believe by certainly 2028, 27 maybe timeframe, we'll be seeing these types of topologies being introduced to inverters that are actually going into vehicles. So that brings me to the end of the presentation. So if I stop sharing now and put the camera back on.
It's great, Dan.
Okay, thank you.
Thanks very much. Yes, thanks very much. Very, very interesting and lots of new stuff even for me to learn and how these things are evolving. So I'm gonna open up the floor to Q&A, but before we do, I did have an offline question that came in from someone, people who couldn't attend today, and she wanted to ask. It's a broader question around the supply chain bit. I think it also reflected on the slide you put with the pyramid and the OEMs in the center about where you think the UK has a part to play in this supply chain. You know, what's the thing we're doing here? We say, you know, and that's the UK contribution to the global picture.
So the one thing that springs to mind from the UK point of view, I mean, obviously we don't have lots of very big car makers like some other countries have. But what we are seeing is with third parties that I alluded to on one of the slides. So in third parties, I'd include universities, I'd include companies that are developing module technology. There's a lot of activity in the UK. So we have one project that's moving forwards very, very well with our die, where a module has been developed and it's also being produced in the UK by a UK company. The die is being sintered onto the base plate. And this is actually for a German OEM. So you have a situation where the research and development is in the UK, and potentially this can be used in German OEM cars in probably 2027, 28 timeframe. And again, this is based on one of the newer topologies I mentioned. So this is a free level inverter.
That's very good, and I think it's something that I recognize as well is that we have a very innovative culture in the UK, and it's something we need to nurture and expand and explore, and especially through our academics. And having been at the University of Warwick, so with the likes of Professor Phil Morby, who you know champions the cause as well, it's great to see that as well. So okay, so to the audience then, do you have any questions you'd like to pose to Dan?
Or people can send them online afterwards.
You can do that as well, yes, for sure.
It's no problem. Okay.
Okay, oh, there is a hand raised. Kashif.
Yes, hi, Daniel.
Kashif, we can't hear you. Yeah, that's better.
Can you hear me now? Okay.
Yeah, perfect.
Yes, Daniel, thank you very much. Really informative talk. So thank you for that. And so with the new sort of model developing, does it mean that OEMs are now preferring to work directly with the likes of semiconductor suppliers and tier twos?
So yes, well, I would say with the new ecosystem, it opens the opportunity up to more people. Yes. So I think if you look at some of the deals being struck between traditional tier ones and semiconductor companies, there's probably some unease with some tier one suppliers because historically they've completely dominated vehicle subsystems, and this is no
Sure.
longer the case. So as I mentioned in reference to the previous question, I mean, the two companies that have developed this module for a German OEM aren't big companies. They're, you know, that there's maybe 100 or 120 people in each, and they've managed to reach into a very major German OEM. So to answer your question, yes, I think it opens the opportunity up for more
Of
people.
course, absolutely. And are those guys manufacturing the modules themselves, or is that like a shared manufacturing capability between the supplier and the OEM?
So I think the project that I'm involved in, at least, I think there's a chance the module will be made by the company that's involved already. Yes, it could be produced in the UK. Yeah.
Sure, exciting. Thank you.
Yep. Thank you for the question. Thank you.
Yeah, thanks for the question, Kashif. And I agree. I think it's exciting, especially certainly over the last 3 or 4 decades, where these large tier ones have had a bit of they've become a barrier to some smart startups and smart,
Yeah.
innovative activity happening in the lower tiers of the supply chain. So it's somehow good to see that there's going to be a shift as well, and it's nice to see that the OEMs recognize there's a need to delve deeper into the supply chain.
Yes.
Thank you. So any go on, Dan,
No,
please.
let's go on. That's fine.
Please add to it. Yeah.
No, I was just going to say, and it reaches into different areas of the vehicle as well. I think chassis electronics is another area potentially, and particularly things like software. People with very novel concepts and smart ideas have a better chance to find a way in, I would say.
Very good. I had a question. You mentioned it's a wide band gap, of course. We've got silicon carbide, which is happening, and we've also you mostly mentioned gallium nitride. Where do you think the transition point is? Is there going to be a switch to that, or do we still feel that's a way away from being realized in terms of high volume usage?
You mean the transition from SiC to GaN?
Yes. Is there going to
Yes.
be one, or are they going to be in parallel, or?
Well, that's the golden question. So I think the reason GaN is interesting for potentially for people is if you look at the process, GaN can be produced on silicon substrates, and it can potentially very quickly be produced on 12-inch wafers. So it comes down to cost. So
Yeah.
I think there's an expectation with some car makers that GaN can be quite closely aligned to standard silicon in terms of cost. Where silicon carbide, because the processes are done at higher temperatures and the material is so hard and so difficult to work with, that you'll never have this parity, or at least in my view, with standard silicon. So I think that's what's driving the whole GaN idea. But things like 3-level inverters, we've got customers using silicon carbide, and the properties of silicon carbide, it performs very well at high frequencies and actually has better thermal conductivity than GaN. So for traction electronics, it's very, very well matched and well aligned. So we'll have to see, I think.
Yeah.
See where the cost and reliability of GaN is in 5 years' time, for example.
Okay, that's interesting. Yeah, 5 years. Still a way to go. So I think also, I mean, I was down in the Welsh cluster, and I visited the Compound Semiconductor Applications Catapult and the new CISM facility at Swansea University. And there's some fascinating, again, when we talk about research and innovation happening in the UK, it's some fascinating investments going on that really look very promising for the likes of ST to get involved with and make sure, we can leverage where some of the early work is going on. Is that something that's important for you?
Yes. So from our side, the UK is recognised as a very good hub for innovation and research and development. And at least in my team, there is an intention to increase the presence a little bit in the UK. So we'll see how that develops.
Yeah.
Yeah. So because it's critical to follow these kinds of trends, and
Yes.
So that we're developing the right products.
Yes, absolutely. And the shift to 800 volts. I remember when I was at the University of Warwick a few years back, we were talking about high voltage systems, 5 or 6 years ago, and whether they were realized. And it's great to see now these breakthroughs coming just because of the benefits with efficiencies and so on. So yeah, so I think it'd be interesting to see what happens beyond 800 volts, because I think some of the other non-automotive applications may drive even higher voltages, right?
Yes. Yeah, we'll see.
Yeah.
I mean, that can create a headache though for semiconductor companies, particularly where things like creepage and clearance are concerned, and how you house the products.
Yeah.
But yeah, we'll see. Yeah.
Very good.
Okay.
Okay, so one last chance. Any more questions? Otherwise, we'll start to wrap up. Okay, then let's wrap up. So 1 or 2 notices from my side. So first of all, Dan, thanks very much. I found it a fascinating
Thank you.
Presentation, and great to see the trends and understanding the trends of the industry as well, because that's one of the things we want to get across in these talks, is get our experts to talk about where the industry is moving to and where the innovation is happening. So thanks very much again.
It's a pleasure. Thank you.
Okay. I'm so just going to share my screen. A couple of notices. The next big one for us is, of course, the AESIN conference. And this is on the 21st of September. So hopefully you can all see my screen. The 21st of September at the National Motorcycle Museum, or Motorcycle Centre as it is now. We've got a great lineup of speakers already announced. We have a number of keynotes ranging from Professor Alex Moussakitis from Jaguar Land Rover, who's a program director for cybersecurity, to Colin Dillon, Colin's a very impressive speaker who's coming all the way from Canada to talk about some of the initiatives for the Canadian supply chain and some of the smart stuff that they're doing there, which I expect to be quite a catalyst for a discussion at the conference. Professor Matt Boyle, who has been chairing the DER ICs, is going to be presenting as well, and David Skip from Ford, who's also the chair of the UK Automotive Council CAM Mobility Work Group. I won't go through all the speakers, but I will scroll down so you get an idea of the prominence we have, from professors to directors to chief engineers to CEOs. So we've lined up some list here of people that are going to be at the conference. And so if you haven't registered, I urge you strongly to go to our website and register. I will leave a link. In the chat as well, so it makes it easy to register. The conference is free to attend for members, and if you're not a member, it's only £99. So it's not a huge amount. But if that seems a bit challenging, then of course you're welcome to become a member, in which case you can get in for free. One other thing to note is that we have opportunities for sponsorship still open. We are getting to fill those quite well now, so there are still some available. And if you are interested, please drop me a note or get onto the conference website, and you can download the sponsorship guide as well. Now, with that, I'm just going to stop sharing my screen so you can see me. With that, I'm also just going to announce when our next Tech Talk is. Just give me 1 second. I'll get to the page here. So our next Tech Talk, again, if I share my screen so it's very clear for you, you go to the website, you can see this. Our next Tech Talk is actually on the 7th of September. And again, related somewhat to the topic of today, Rob Harper from this Compound Semiconductor Center is going to be talking about the advances in wide bandgap technologies. And so very pertinent to the topic we were touching on regarding silicon carbide and GaN. So please join us for that. If you haven't, please feel free to go to our events page, register, and make sure you join us for that as well. And we have 2 more talks planned for this year. The one on the 5th of October is one from Matt Evans from Cadence. around the simulation of thermal properties in electric drivetrains. And the final one is still open. If somebody wants to register for a Tech Talk, then please drop me a note and we can make sure you get onto that final Tech Talk of the year. So with that, again, I just want to thank our speaker, Dan Murphy, and thank you all for joining. We will have the recordings available for members on our website. For non-members, we'll have a redacted version available through our social media channels as well. For that, thanks very much, and I hope you have a very good afternoon.
Okay, thank you.
Take care.
Thanks.
Thank you.
Thank you.